Today we are very glad to meet here Professor George Mackey from Harvard University. And he will be talking about representation theory and quantum mechanics, recent development in somewhat unconventional approach. I cannot tell you.
Okay, well, this is a large part of this lecture is going to be a review of things that I've known a long time. But I hope at the end to tell you some beginnings of the kind of thing that I'm going to be worrying about now. What I'm going to try to do something rather ambitious in a way, because I've always regretted that mathematicians, so few mathematicians have any knowledge of quantum mechanics, although I feel that all the people in the world are best qualified to properly understand it, because it involves some rather sophisticated mathematics in a way that physicists sort of use in a sort of slipshod way. You've got a deeper knowledge of what's going on if you're a mathematician, or if you're about to try. And the tool in doing this is the theory of unitary two-purpose space in Hilbert space, which many of you know a great deal up to now. And, but of course, that's sort of sense I want to expose both of these subjects to people who don't know either one, which is a rather daunting thing to try to do. And the way I've started to try to do it is by giving you baby versions, at least of the group term, I think, or at least the result is smart. So I'm going to try to tell you about a rather not so easy theorem that I'm very proud of discovered many years ago called the Impermitivity Serum. So I'm going to give you again a baby version. In fact, I can formulate that so I can give you I can formulate the theorems which are almost obvious. I would even prove them here if I weren't so short of time. So I'm going to suggest that these theorems that I state without proof can be proved by you tonight or in an hour or so or less. So if you really want to understand this talk, you've got to do the exercises. But I hope in this way I can tell you what this theory is about without going through the hours of lectures it takes to prove it and everything. Because the baby version, essentially finite group version, can be proved easily by any properly educated mathematician. Okay, so this means I'm going to do several separate lectures and then try to talk about the relationship between them all. This and this are going to be separate parts of pure algebra. I'm going to indicate very briefly. This is a review of what's called Hamiltonian dynamics in Poisson brackets. And then when I've got these explained, then I will try to explain the original formulation of quantum mechanics by Heisenberg, Dirac, Bohr, and Jordan. Although it isn't a very satisfying formulation, but they have the central idea that they tie together commutator brackets of operator theory with the Poisson brackets of classical mechanics. But then I'm going to go back and show you how to start over again in a sense, and using this part, which is the representation theory that we need, you can start to extrapolate a much more satisfying result. And then I'm going to talk about all of this I've known for quite some time. Some of it, and then I'm going to go on and what the time is remaining, so how I'm trying to extend this now, and what kind of had some success. All right. Well, I'm going to start off. I'm going to put the following. We'll start with a finite abelian group. Finite. Now I'm going to remind you, I think most people know, that given a finite community group, there's a sort of a dual group. There's something called a character group, which is simply a homomorphism of the group into the complex numbers of modulus 1. That's the definition of a character. representation, which is called a dual group. And the dual group is actually isomorphic to the original group. Although that's not true for some of the fancier groups that I'll refer to later. But for a finite abelian group, it's like a vector space in a dual. There's no canonical isomorphism. There's a different group. Now what I've done here, in that context, I've defined two representations of the group. This is the so-called regular representation. I have to take all of the functions on the group, all of the complex valued functions on the group, and then define a family of operators by translation. If I define use of x of f, I'll evaluate it to y, to f of yx. It's a translation operator. That's totally going to be a homomorphism of G into the group of operators on this vector space. You don't call it f of G. Actually, in the infinite case, you take the square sum of the function. I'm not getting into this complicated thing. All right. So we have, and here's another. This is clearly, in fact, if we do make f of G into a Hilbert space in the obvious way, then these are both unitary representations of the group. Both operating on the same space, infinite f of G. So I have two representations operating in the same space. Now, exercise 1 proves this identity. This is straightforward computation. But this is, in fact, a baby version of the Hermann-Weyl form of the famous Heisenberg commutation relation, which that will be explained later. It tells you how to connect with other things. So there is a baby form of the Heisenberg commutation relation. And now I want to talk about a Spectral Theorem. This is the a very baby version of a thing which I call the Impermitivity Serum. But it goes by the physicists refer to it as the uniqueness of the solutions of Heisenberg commutation. What is that about? All right. Suppose I now, instead of taking these very specific representations of G, I take an arbitrary pair of representations of G in the same space. But not quite arbitrary. I make them satisfy this. So take an arbitrary pair of representations of my group G to satisfy the Weyl form of the Heisenberg commutation relation. What can I say about that? Well, the answer is very simple. Essentially, this is the only possible thing satisfied. Now, that's not quite true. One is, given any solution to the Heisenberg commutation relation, you can write the whole space as a direct sum of subspaces. And on each of these subspaces, the representation is equivalent to what I described. So there's one irreducible solution, everything else can be built out of the most obvious sort of way. All right. Now, how about the proof of this? I mean, that is an exercise for you too. But the exercise becomes easier if I generalize it. If I first change the form of the question, and then generalize it. Remember, once I've changed the form of the question, well, you might as well drop the commutativity. I'm going to change the form of the question so I don't use duality. I'm going to do that by a very simple trick. First of all, I forgot to mention when I talked about duality that when you take the dual G root of the group by taking the group of all characters, then you can reverse it, because if you now consider this U group and take this character, now instead of varying x for a fixed chi, let's vary chi for a fixed x. That's what we see as a character of G root. We go all this way. So you can look at it either way. Not only is G root the character of G, but G is the character group of G root. All right? Now, having done that, let's take this representation that we have here of G root. And I want to make it into another kind of object on G. And you say, all right, now let's think a minute. Here's this V chi on here. It's going to be a representation of this group G root. Now, this is kind of confusing. But now remember now that the G root is the character group of G. G equals G double root. And by a very elementary group representation here, every representation of an abelian group is simply a direct sum of characters. So that means that I can now write Vx, V chi is simply a sum of characters of type, those are defined by element x of g. And it's Px is projection in the Hilbert space. I've simply written this representation as a direct sum over the dual group of these one-dimensional representations. And this Px is simply the projection on the subspace of all those on which the representation reduces to the character implied by x. So I can describe my V chi completely by objects on the original group G. Namely, yes, I'm not saying yes. Yes. You see now, what I have now is for each element on the group G, I have a little projection of it, a Px. And knowing those Px's, I can reconstruct V chi in this way. But now from the very definition, these Px's have a certain additive property. Px and Py are orthogonal projections when x and y are distinct. And the sum of all of them is simply the identity of them. That's so-called, that's something I call a projection value measure. Now, just for later convenience, I'm now going to drop outside of this finite context and just define projection value measure for you in general. Now this is going to involve a very minor analysis of the definitions, but let's just do that because that's going to be the easiest thing to do, then come back again. A projection value measure on a sub F is an assignment of a projection operator TE to every subset E of S such that P of such that whenever E1, E2, etc. are disjoint, then P, E1 plus E2 and so on equals E1 plus E2. Now that acts like a numerical, that's what we call a projection value measure. But also we might put on the condition that P, E1 tap, or the P, E tap F equals PE times GF, so all E and F. P of the empty set equals the zero projection. P of the whole space is the identity. That's the formal definition of projection value measure in general. Now what I mean by this ever, by the quotation marks around the ever. Well, if you have a discrete space S, that's literally true. If you don't have a discrete space S, you have to assume it has some sort of measurable structure, and then you want only measurable sets. I don't want to go any more into the analysis. I've been helped out. Over here, I'm just going to apply to a finite set. So I really do mean ever.
What do you mean by zero?
What?
What is the zero?
Oh, the zero project, zero elsewhere.
But S, everything went to a single element?
Yes, I mean you assign the identity element to the whole space. You assign the zero element to the empty set.
S does not have a zero element.
What?
S is just a set.
No. Wait a minute. Of course that's right. Where have I denied it? Oh,
You haven't said what the vector space is.
It's not some Hilbert space.
what?
You space.
Yeah, I'm assuming my vector space is the Hilbert space. These are all operators in some Hilbert space.
On functions on S?
What?
Is it functions on S? What does it have to do with S? Is it functions on S?
What? It's what functions on it? No, the Hilbert space is not functions on it.
What is it?
It's an abstract Hilbert space.
What does it have to do with the set S?
What?
What is the relation to the set
All right.
S?
She said as an
That's-
indexing set.
It's like saying what is the relationship of the Hilbert space of representation of the original group? It's a mapping from subsets of S into projection operators in a Hilbert space, certain properties. It's in a sense an analog of a group representation, where instead of representing a group by invertible operators, you represent a Boolean algebra of steps by projection. Now, whatever the space S is finite or countably or discrete in any sense, then the whole thing is determined by P applied to one point sets. And then this is just a fancy way of talking about a decomposition of the Hilbert space as a direct sum parameterized by the elements of S. However, when we go on to the infinite case, that's not going to be good enough. Because very often some of the most interesting projection value measures are zero on all one-point sets. So you have to consider the non-one-point sets, but not at this level. But later on, I'm going to have to bring that in. So that's why I want to make the definition once and for all. Now, this definition involves analysis at this point. But when over here, the specialization does not involve analysis. It's just a trivial way of describing explicitly an operator to determine the representation. So in any case, so I'm going to end up over here, my S is going to be G, the original group. So I started off with two things, the representation of my group G and a representation of the dual group G root. But now I've shown how the latter can be turned into a projection value measure on G. So now I have two objects on G, a representation of G, projection value measure on G. And I don't need G root anymore. I need it for a minute. What I can say now is you can now wonder, okay, suppose my original U and V satisfies this Heisenberg commutation relation. What does that mean about the pair consisting of U? I've just pointed out to you that this pair determines a pair like this. What does this condition translate into? Well, that's one of the most interesting things up to the day. In a certain sense. It translates it very beautifully and simply. Maybe I should pause right down. Translates it into UX PE UX inverse equals P translated by X inverse. This is totally equivalent in this context over here, totally equivalent to this relationship. So if I want the most general pair satisfying this, just forget about G root and ask for the most general pair of the P and the U satisfying this relationship. Okay, so that's a triviality. You can go verify all of this without knowing anything other than these definitions. Everything I've told you is essentially trivial. What's not trivial is the generalization in the case, but I'm not going to try to get those over to you. No? All right. So we have this relationship. I'm going to put it up somewhere. Let's see, I'll stick it up on top of all of that. UX, But checking this, you suspect it's not quite right, and I should have put an X inverse here and X there, and you're probably right. I never can get these in a straight and systematic way. But if it doesn't quite work, if you don't find a contradiction, you're supposed to change one of these inverses to the non-inverse. Okay. So this relationship is equivalent to this one. But this one makes sense even when well, first of all, this would make sense without mentioning G root. And secondly, it doesn't require the G even be commutative anymore. Any finite group, this relation makes sense. So I can ask the same question. Given an arbitrary group G, given a representation on it and a projection value measure on it in the same Hilbert space, what are all the possibilities? Well, the same theorem is still true. It's unique. But now it's fucking trivial. And I'm not going to give you the details. I'm going to tell you how to do it. Well, what you notice is the following. Okay, we've got this Hilbert space, and we've got this projection value measure defined on G. But everything is finite now. So this is totally determined simply a direct sum decomposition of the Hilbert space. There's one element for each, say, X. With one Hilbert space for each group element. Well, now, what is this? Now you can reinterpret what this identity means. It means something very simple. It says that each UX takes let's let HY be the subspace corresponding to Y, to GY. It says that UX operating on HY is just equal to HXY. So if I get that, I can start it back. It just commutes the Hilbert spaces. Well, now, you just go home and meditate about that, and you will see that that it follows from this that the whole thing is totally determined up to equivalence by the dimension of this Hilbert space. First of all, these Hilbert spaces all under that same dimension. Knowing that dimension determines the whole structure. You just look at it hard, and you see that. So there's exactly one answer for every dimension of the Hilbert space. You take it to be a one-dimensional Hilbert space, and it's the irreducible thing we started with. And those are the only possibilities. So we know completely the solutions of the vile form of the Heisenberg commutation legend locally compact, for finite community groups, and that can be generalized into something that doesn't involve duality. Okay. Now, when I'm about to leave this, I have to say one more thing. I can generalize this still further. Suppose instead of just having a group, we have any finite group G, but now we're going to assume that we have a group B, that G is given as a transformation group on some other set S. S can be an arbitrary set. Now G acts on it. But I can still, and now I'll define a projection values measure P is now going to be defined on S. And our representation is still a representation of G. But I can still write down this identity. That doesn't make sense. So I can ask, well, let's now try to find all possibilities in this case. Well, now it isn't quite so simple. Well, first of all, it's perfectly clear that you only have to consider the case when G acts transitively on S. And all other cases can be reduced to that. You just break up into separate orbits. So we're only interested in the case when G acts transitively on S, but that means that S can be identified with G mod H, where H is a subgroup leaving some arbitrarily chosen origin in S space. All right. Now, but once again, you can look at you can see that given this, just gives us a decomposition of this Hilbert space, and once again, that the operators just permute these amongst themselves. But now there's more than one possibility because there's an overlap. Because it's possible now for in fact, it's going to happen now that whenever H isn't the identity, that there's going to be a Hilbert space which is carried into itself by all of these cells. So this is going to abolish things up. So it isn't quite as trivial. However, it's something that's easily analyzed. If you sit down and think it over for a while, and you discover the following. You discover the following thing. You choose an origin, S naught, and let H, S naught, be the subgroup of G leaving that fixed. Then if you now just go back to that subgroup, HS naught, and look at U only on this you have a representation of the subgroup. Now, in a slightly more complicated, but not very difficult argument, you can now prove that once you know the subgroup and that representation of the subgroup, you can rebuild all those things. So now you no longer have uniqueness there. You have a different possibility for every possible unitary representation of H given HS. You just classify the representation of HS, and you can find all those pairs. Now that is the baby version of what I call the impermitivity serum. Now that's true with much greater generality, but it's not so easy to prove. So the impermitivity theorem classifies all pairs consisting of, starting with a transitive transformation group, considers a set of all pairs consisting of a projection value measure on F, a unitary representation of G, related by satisfying X. Now there's no uniqueness theorem for that, but there's a classification theorem, and that classification theorem is called the impermitivity theorem. Turns out in particular that every possible representation of the subgroup HS naught occurs. So you have a natural way of passing from representations of a subgroup to those of the whole group. And that's the thing called inducing a representation. There's well-known in the earliest days, Frobenius, that you have this natural mapping going from any representation of a subgroup of the finite group to a representation of the whole group. And you can regard the impermitivity theorem as a characterization of the representation of the whole group. You can get it that way. The impermitivity theorem is regarded as a characterization of induced representation. And the process of inducing a representation from a subgroup to the whole group, as Mark will tell you, plays a prominent role in the theory of representation. In fact, he just written a book on a generalization of that process. But this is the baby version to be the algebraic relation. Ego. Okay. Now let me turn to another topic for the moment. Put another aside. So anyway, I have another algebraic topic. I now want to discuss uniqueness of the Heisenberg commutation rule, not as a Weil form, but its original Heisenberg form, where the basic version of it. Oh yeah, here it is. P and Q are now operators. PQ minus QP is 1 over I times the identity. This is a slightly simplified form of the kind of Heisenberg commutation related to the quantum mechanics. And this relationship is very closely related to this the way that I want to explain later. So now I'm going to tell you some curious algebra you can do. And this is something, by the way, that I've learned rather recently. That once you have this pair of PQ satisfying this, it turns out for many, many practical purposes, like quantum mechanics, to be convenient to replace this pair of self-adjoint, these usually self-adjoint operators, by another pair, I'll call AB, defined by this connection. These A and B are what the physicists call creation and annihilation. So this looks like a sort of a trivial change of basis, which it is. But it has amazing properties. I'm going to give you one of the simple things right now. There's a certain theorem you can use, sort of a trivial theorem you can state, that if you take, of course, the A and B on the one hand, and Q and B on the other hand, generate the same two-dimensional subspace of operators. And it's a very simple thing to say to prove that B and Q will satisfy this if and only if A and B satisfy this. This is almost the same thing as a Heisenberg commutation. The only difference is that we usually have non-self-adjoint operators and the I in here, that's the identity itself. All right. Now what I want to do is to say a few words about what you can do with this. This is the pure algorithm. In order to make it pure pure algebra, stay away from the upper spaces and this. And I won't even assume anything like some adjoint. I'll get abstract. We'll assume that A, B, Q, and P are operators in an abstract vector, complex vector space. Then, one of the first consequences you can draw is this. And this is proved by a very trivial induction. Oh, come on. I'm now going to give you things you can go home and prove as exercise. Namely, this thing you prove by trivial induction is the following. A, B to the n minus B to the n A is equal to n times B to the n minus 1. I just want to differentiate the power. That's a consequence of the entirely consequence of that. All right, now I want to make now I'm going to make one further assumption. I'm going to assume there exists phi contained in X, phi not equal to 0. A of phi equal to 0. This is when phi is called a vacuum vector, and A is an annihilation operator that annihilates the vacuum. Now I'm going for the B to call creation. All right, now this and this, we can now prove the following almost immediately. First of all, let's now consider the vector space generated by phi, B of phi, B squared of phi, etc. We run out. Well, first of all, I'm not going to give you the proof, but the fact that AB minus BA cannot hold a finite dimensional vector space because the trace of one side has to be 0 and the trace of the other side can't be 0. It has to be an infinite-dimensional vector space. You can use that very quickly to prove that no B to the n can be 0, no B to the n phi can be 0. Secondly, obviously this vector space is carried into itself by B. How about A? Well, using this, you can show that it's carried into itself by A. So this is invariant under A and B, and hence under B and Q. So here we have an invariant subspace. And all of the A's and B's are, this vector subspace has the property that B carries each of these objects into the next one. And A carries each of these objects into a constant times the one before it. But now if we if we assume our original pair of operators were irreducible, then this will have to be the whole space. It's invariant. And now I've got a basis for the whole space that tells me very explicitly what A and B are and what P and Q are. And I've shown there's only one possible solution. So that's the uniqueness of the Heisenberg commutation relations, the way it's usually presented by the physicists. Not only that, but it turns out that if you take the operator P squared or Q squared in physical applications, has great importance. This diagonalizes. B squared plus Q squared carried over to AB plus BA. Now, B is going to hit you up one, A is going to hit you back again. So AB carried each of these bases on to the lower set. So does the other way. And you diagonalize this upward, which is a thing that's very important for this computation. Okay, so I've now said all I want to say about this part of the board. Now I want to get over here. Start learning some physics. First, I want to refer back to classical mechanics and the so-called Hamiltonian form of the equation of motion. Suppose I have a study of the classical mechanics of n interacting particles, say in Newton's planetary motion, whatever. then it's convenient. That's not Q1 up to Q3n. The coordinates of all the particles. So n particle, each particle has 3 coordinates, the x coordinate, the y coordinate, the z coordinate. I was going to lump them all together as Q1 to Q3n. And then T1, T3n. Well, famous Hamilton's equations of motion say the following, that Newton's equations of motion, or the equations of motion in very general situations of a system of n particles, can be, not always, but essentially in a huge number of cases that are important, can be written what's called Hamiltonian form. What does that mean? It means that a single function, h, q1, q3n, p1, p3n. I don't even have to define the I'll get into the p's out at this point, because they're defined by the equations, actually. Such that the equations of motion take this form. This is a system of fixed-hand equations for the time variation of the q's and the p's. Actually, in simple cases, p is just the mass multiplied by d by the corresponding derivative of the corresponding coordinates. That's not even concerned now. In fact, if you just analyze these equations, you can pull that out of it, and the Hamiltonian has the right form. But these are, I say, Hamilton's famous equations of motion. And the most convenient thing to use in going from classical mechanics to quantum mechanics. So now, I want to be motivated, not the way with the Ricci done, but I want to motivate the introduction of this option. You have 2 different functions of the p's and the q's. Then you can create a new function of the p's and q's by this formula, called the Poisson bracket. And if you do it in terms of the right differential geometry notion, you can show it doesn't depend on the coordinates. But I haven't got time to explain that. But you can motivate the introduction as follows. You say, suppose I take an arbitrary function, g1, of all the p's and q's. Then by just using advanced calculus, you can compute the time derivative of that function when the q's and p's satisfy this differential equation. And we work out the advanced calculus, which is a straightforward exercise. You get this formula with g2 replacing h. So you start doing that, and then you notice that this formula makes sense for the by you put an arbitrary function there, and there you have a nice little formula for creating new functions of p and q out of O. Now it turns out so just take instead of all smooth functions of p and p, you can use, and I have a way of combining to them called the Poisson bracket. And the great interest of that is that this turns out to go over into quantum mechanics and simply work their comes to it. Not that I won't quickly come. But now, but I want to point out one thing, using this thing as a fundamental object, you can simplify these equations and make these equations even more symmetrical. Because it's a very simple computation to show that now you can that dqj dt is simply the Poisson bracket of j with h, and dpj dt is the Poisson bracket of pj with h. And that's just another way of saying this, once we get this definition. Okay, so that's it. Then finally, another thing that's very important for the passage to quantum mechanics is that if you look at the Poisson bracket of the p's and q's themselves, you find that the p's all have a 0 Poisson bracket. Q's have 0 Poisson bracket, and the p's and q's have something have 0 Poisson bracket, except when p is equal, when I is equal to j, and then it becomes 1. Now this is very close to the Heisenberg computation. Okay, so that's Hamiltonian dynamics brief. Okay, all right. Now, having done that, what do I want to do next? Okay. Now I will mention that. Now let me talk about the new and old. The old problem, old quantum theory. And quantum mechanics. Well, in 1900, more or less, distinguished German physicist named Max Planck made a very curious discovery, studying electromagnetic radiation and trying to get formulas telling you how the radiation for certain kinds of things called black bodies vary to the temperature. And we used the method known up to that time for dealing with heat temperatures, thermodynamics, and so on. He was led to a formula which was right only at one end of the spectrum. A man named Dean found another formula which was right at the other end of the spectrum, by different reasons. The question was to reconcile these things. Well, Planck's great discovery was that if you took the classical mechanics they were using in their things, in fact, the basic thing used in classical mechanics is a very simple thing called the harmonic oscillator, which is a thing whose Hamiltonian form, the H is equal to P squared over 2m plus Q squared over 2mu for m and u are positive constants. That's the Hamiltonian that governs, say, the vibrations of a weight on a spring. And the solutions are all sort of periodic functions, back and forth. Yeah, but that's the Hamiltonian form. But what he discovered was, in the analysis he was making, that if he sort of arbitrarily, without any really good reason, assumed that the energies that this oscillator could take on were just discrete multiples of the smallest energy, then he could explain both ends of the spectrum. But it was logically inconsistent to use classical mechanics and then this arbitrary discretization. And then over the next 25 years, various people found the same trick that we used to explain other things. The so-called photoelectric effect, things like sticky, solid. In every case, you just make some arbitrary quantization assumption. And lo and behold, you could explain certain formulas. But the two things here that didn't make any real consistent whole. And physicists were very eager to do something about that, and particularly gradually dawned on them that somehow classical mechanics were going to have to be changed. And the first person to make a step in the right direction was Heisenberg. He was a very young man. He just got his PhD. He was the assistant of Max Born in Göttingen. And he wrote a little short paper which suggested a way. Very obscure. I read the paper recently. It's very hard to understand. It's not very clear at all. But he decided that he wanted to have a new mechanics in which the variables P, Q, H, and so on were not numbers but matrices. His reasons for wanting matrices, I don't want to take time to try to explain. And he didn't do it right anyway. He didn't know what a matrix was. He wanted a square array of numbers where the indices corresponded to states of an atom or something like that. And he invented a peculiar way of multiplying them so he could do algebra with it. And it was Max Born who pointed out then that he rediscovered matrix forms. but then this paper of his was read by his boss. He was Born's assistant. Born was a middle-aged man. And he was one who thought, hey, you did this. Born got very excited when he discovered that his matrix multiplication. So this really means something now. But also the Englishman Dirac got a preprint of the paper and started thinking about it. And he sort of had the cleanest idea. He made it much clearer than Heisenberg did. Well, I'm not going to go through the whole paper. There were several papers by Dirac, Born, Jordan, and so on. But the upshot of it all was, they were going to have a new mechanic. The new mechanics they were going to have to explain all of this was going to replace variables by operators. And Dirac's idea, which is much better than anyone else's idea, direction was that when you made this switch over, you would carry over all the rules of Hamiltonian dynamics. However, what would replace Poisson brackets? He decided they should be, right. Well, the big problem they saw was since if they were going to carry over the laws of classical mechanics to matrices, what are you going to do about the fact that matrices don't need to commute? And Dirac essentially solved it by finding out that H is going to be a function of the P's and Q's, and if you know if H is any sort of a polynomial or power series, then you know how H commutes with things is enough to know how the P's and Q's commute. And he said what we should do is replace the Poisson bracket by the commutator bracket of two matrices, or by a constant times it actually. And the constant, when you work things out, turns out to be Planck's constant, divided by 2 pi. So the upshot was that you, so this is what they tried to find out, and there was still when it worked. Because now, let's go back to this. If they went back to the Planck oscillator, and I don't want to simplify things too much to make this part simple, but let's just look at the special case when these two numbers are equal. So you get that p squared plus q squared worries on. Then this analysis that I gave over here with the A's and B's actually lets you diagonalize the energy of them. I mean, this operator H, which corresponds with energy in classical mechanics. We've just seen, and it follows from the simple model analysis that I just gave that if you choose the P's and Q's for this matrix is diagonal, well, you will simply get the equally spaced thing at the Planck constant. And so they started playing with this idea of taking classical Hamiltonian. Now they're awfully difficult because if H is an arbitrary function of P's and Q's, it isn't always clear how you're going to work in two non-commuting operators, even if you know how they commute. But you can do it in the special case, which is very common, for H is the sum of 2 functions. One only is a P, one only is the Q's. Now these relationships would imply that the operators corresponding to Q's all have to commute with each other. And it's easy to form functions of each of the commuting operators. Same as the P's. But then in the end you're going to have to cope with other things, but here you assume that P and Q satisfy the Heisenberg commutation relations. Because of the Poisson bracket formulas. And so in the end you actually get a workable procedure. And you can work it out quite completely as a Planck oscillator, you get this mysterious answer to Planck. And then with a little harder work later on, they were able to explain the spectrum of the hydrogen atoms. Now, that was the harder work out, but you explain around with people who are very ingenious people. They're in all of their beautiful papers. And I don't want to. Now we go. Yes, well, okay. Taking longer than I hoped. I have a push on. So I think I'll just mention Schrödinger. Schrödinger hadn't even come on the scene yet. But then Schrödinger was basically because turns out that one very interesting solution of the Heisenberg commutation relations is to take Q multiplication by X and P 1 over I partial with respect to X. And Schrödinger, by quite other reasoning, was led to take a Hamiltonian and substitute these things for P and Q and find the eigenvalues of that operator. But he did this from a totally different point of view. When he was first, at first he admitted he knew about what Dirac and other people had done, but somehow he knew it had to be right because of the result, but he couldn't see how to connect them because it took a while. And in those days, most people were very ignorant of the connection between matrices and operators. It wasn't at all obvious to them at first. just working with a special solution of the Heisenberg commutation relation, so that you're going to get the same eigenvalues in Higgs. Okay, but this is all, when you try to make this rigorous in an infinite dimensional case, you run into all sorts of problems. And an extremely important advance from a mathematician's point of view was made by Neumann. And I want to get a few words about that now. I should say that Schrödinger's papers came out about 6 months after the first Heisenberg paper. I don't have time to break all that. All right. Now, Neumann was an analyst, and he knew Hilbert's work. Now, let me say a word about that. Way back earlier, way back in the middle of the old quantum theory, Hilbert proved the famous Hilbert Spectral Theorem. What did that say? Well, in our language, what that says is the following. If you take a symmetric operator in finite dimensional space, everyone knows they can always be diagonalized. And that the operator is determined with an equivalence by the values of the multiplicity of the eigenvalues. But if you take an infinite dimensional Hilbert space and have a separate operator, you can't do that. It's easy to give examples of separate operators that have no eigenvectors at all. What they call continuous spectrum. But one theorem is very trivial to prove in the spirit of all of this. It says you're in a finite dimensional vector space, then every subordinate operator is uniquely associated with a projection value measured on the real line, one that's concentrated in a finite number of points, namely the spectral values. And given the projection value measures, you immediately reconstruct the operator. Well, in essence, what Hilbert proved, his famous spectral theorem is that if you admit all projection value measures, including those that aren't concentrated in any points, then once again, you've got a perfect one-to-one correspondence between projection value measures and Hilbertian operators. That's the Hilbert spectral theorem. The only proof for bounded operators, but the Neumann is shown independently, more or less, extended to some unbounded operators. It's important because P's and Q's cannot be bounded operators. All right. And then once Neumann had that, he gave a very rigorously stated, completely mathematically satisfactory formulation of quantum mechanics. But he said, but the Neumann's formulation of quantum mechanics is following. That given any system, any dynamical system which you want to look at quantum mechanically, there will be a Hilbert space, and there will be, for every observable, there will be a self-adjoint operator. For every vector, for every unit vector phi contained in each vector, there will be a so-called state of the system. What is the meaning of these things? Well, this is something that they didn't have at all. Schrödinger, when he had it partly rejected it for every 2 years. I think neither Heisenberg nor Schrödinger ever understood the Neumann formulation, although he proved that they did it in a very beautiful way. Anyway, he just said, given, so let's not A be a self-adjoint operator corresponding to some observable, and let's phi be a unit vector corresponding to some so-called state. Then, what do we have? Let's pass from A to the projection value measure associated with it by Hilbert spectral theorem. Then, if we apply PA to phi dot phi, this thing as a function of E. A is just the label. E is the set of the projection value measure. Then this as a set function is a probability measure. So we think the idea was that in quantum mechanics, a state of the system does not determine a value for every observable. It just assigns a probability distribution for every observable. And how does the system change in time? Well, there's another. It changes in time by choosing a one-parameter unitary group, a unitary representation of the real line, such that the future of the system given one entity. If I have a state phi and time t equals 0, then the later time, the state has to be UT-ified. Well, now you can spend a whole lecture working out the consequences of these two assumptions, and you get all sorts of interesting results. And in particular, well, you find out that I should say one other thing. Then there was a theorem. At that time, it was only conjecture, but it was proved in 1930 by Marshall Stone. It says for any one parameter unitary group with a unique self-adjoint operator, such that UT is simply the exponentiation of that. And that H corresponds to the Hamiltonian classical mechanics. But that means that now you have a perfectly general way. A state of the system is now not given by a set of P's and Q's. It's given by a vector in the Hilbert space. The observables are not given by functions, P's and Q's. They're given by self-adjoint operators. This is the meaning, the physical meaning of relationship between a state and an observable. The changes in time of the systems are given by one parameter unitary group that's uniquely defined by a self-adjoint operator H. Everything's there. Except you have to know for each system, how do I find H? What are the C's? What are the Q's? And so on. I think time is running very short indeed. So I have to say much less than that's intended. But let me just go on to say very quickly now that Hermann Weyl was the first one to try systematically. Now I want to be very rapid. I have to say several things without going into any detail at all. But let me just say a few of these things. The phenomenon formulation is completely satisfactory, except it doesn't tie in with the corresponding classical systems at all. There is a way of tying in by taking a hint from Heisenberg, because you can in many cases, if you have a classical Hamiltonian, then you're going to get the operator H by substituting partial P with respect to X and multiplicate by X inside and so on. And you can combine the Schrödinger picture with the Heisenberg picture and then fill that in from many problems. But Hermann Weyl wanted to go deeper than that, and he wanted some intrinsic reason for this. It didn't go back to classical mechanics. He wanted, it turned out to be possible to start from scratch. And in doing that, well, see, now I can make this connection, the connection between this relationship and that relationship. Because if you use this connection between self-adjoint operators and one-parameter unitary groups, then you can compute what the infinitesimal version of, let's take this relationship applied to the real line instead of a finite being group. And then, just by differentiation, you can show that the corresponding operators here will satisfy this relationship. So one is when you apply them to the case of the whole real line, then the connection between these two things is one is the infinitesimal version of the other, or the algebra version of the other. But it's much easier to work with the Weyl version, because there you can do a rigorous version. And in fact, as I was hinting earlier, in 1949, I got very interested in all of these things, and I think for the first time proved an infinite version of the impermitivity theorem. In fact, we replaced everything by self-adjoint by unitary representation in Hilbert space. And in fact, everything is still true. Everything that I showed you for finite still goes over. And then so you do have a version of the impermitivity theorem which would imply very particularly a rigorous uniqueness to the Weyl form of the Heisenberg commutation relation. And Weyl anticipated, in fact, he was one who inspired Stone to prove the theorem. to make a very long story short, I will now go on to say that if you start off with that idea and use the impermitivity theorem as a general case, you can do well. You mentioned one. I'm going too fast because I've lost time. I haven't enough time, but. Yes. You see, when you've gone from this uniqueness theorem up to the impermitivity theorem, you seem to have gone very far from anything connected with physics. It turns out you can turn around backwards. And you can start off and say, without assuming any classical mechanics, you could just assume that the Neumann formulation, and then try to decide from first principles what a single isolated particle is like in quantum mechanics. And it turns out that doing that in itself suggests a projection value measure, not coming from, it's coming out of the air. Because the idea is that for each subset of space, there will be an observable, which is 1 when you're in the space and 0 when you're outside it. And that will have to be represented by a projection of Neumann scheme. So you find out that all observables is completely described by a projection value measure defined on space. Then if you assume invariance under translation to rotation, you can get a group representation which you can then compare with this projection value measure. And then again, on purely invariant grounds, you can argue that it must satisfy this relationship. And then it turns out by using the impermitivity theorem in infinite form, you can derive the only possible solutions. And there's one for every representation now of the rotation group. If you choose that to be the identity, you get the classical physicist formulation for a free particle. With one proviso I have to mention. And what is the meaning of this representation of the rotation group? Well, that's what the physicists call the spin of the particle. So in this way, by connecting these things in the correct way, you can derive what a single particle is, starting from practically nothing, without knowing anything about classical mechanics. Now I cheated a little bit because you don't get quite the full thing. Your Hamiltonian isn't going to be the classical Hamiltonian, but it's going to be the classical Hamiltonian is a constant times for a single particle. It's a constant times the Laplacian. What you get is all you do is you have some function of Laplacian, and anything is possible. Now, in order to get the ordinary Laplacian, you have a constant times the ordinary Laplacian. You have to assume space-time invariant, Galilean relativity. If you assume Einstein's relativity, well, you get a different answer. And the one they're using non-relativistic formula. But all that's included in the formula. And of course, knowing about a single particle is not that interesting. You have to go on from there. Well, you can go on from there. And I was going to tell you something. I'm afraid this is going to be entirely preliminary because I simply haven't any time left to go on. But I will just tell you that you can go on and that you can go very far in extending this framework to explain practically everything that physicists do, and I'm working right now trying to go further. And I apologize for not being able to do that. I hope I can crowd this much into the first 40 minutes and then go on with the other, but it turned out that didn't work. So that's it. Thank you for your attention.
Questions, please? You were still on mechanics, or is it on? What, can you tell us a little bit about your new work?
Can I hear you?
Can you tell us a little bit about your most recent work?
Yeah. One paper that just came out last May theory of Lie algebras and the way the physicists deal with what they call quantum fields. And it's really a generalization of this little remark that I made down here about using the A's and B's. So am I allowed 5 minutes to answer this question? What? Okay, well, I give you a rough idea of what this is. This is a paper that appeared at the proceedings of a conference held in San Antonio a year or two ago. The book itself came out last May. And in fact, I have a copy of the paper here that I could, if anybody wanted to make a Xerox of it. What I get in this was simply consider, when I told you about the Heisenberg computation relation, I always did it with 1p and 1q. But you know, for a general homomorphism, system, there'd be 3np, 3nq. So let's now consider the following object. Let's let x be a complex vector space. Now I'm going to work in a purely algebraic algebra format. I can clear what I was doing here. One problem I haven't thoroughly worked out is how to globalize this in a reasonable way. I think I'm on the trail, but I'll do it in that form. Let x be a complex vector space. And let b be, let delta equal plus or minus 1. And let b be a vector space of linear operators AB minus BA is equal to some constant, which I call lambda of A and B, times the identity. By the way, when an example is follows. If in a particular case, A must be plus delta BA, that's what a delta is. If I take delta equal to minus 1, this is this commutator. And if I take delta equal to plus 1, what's called the anti-commutator. The interesting thing is that they both occur in physics eventually, and this takes care of them both at the same time. Okay, now what can I say about this? Well, the curious fact that really surprising is this following theorem is true. Given one of these objects, I'd say a vector space of linear operators, which in every pair of elements we have this kind of computation relation. Then let b squared denote the linear span of all the products all possible products of pairs of elements from B. There are b squared is the element. In the paper, very special page we were discussing earlier, where we just had a two-dimensional, just two operators. That Lie algebra turns out to be the Lie algebra of the 3 by 3, 2 by 2 matrix. Yes. But now the interesting thing is this. Now the proof of this is not as easy an exercise as the other. You can go, you have to break it up into a couple of lemmas that are easy to prove. The whole thing can be done quite easily in an elementary way. But starting from scratch, you might find some help proving it. But it's true. So now the interesting thing is, now form. Lambda beta B is going to be a bilinear form, which is symmetric, and when delta is equal to minus 1, and antisymmetric when delta equals plus 1. But then now let's assume that that's antisymmetric, and we can do then by at least when B is finite dimensional, you can then derive a basis for that, called a canonical basis, in which the pieces all satisfy things like the commutation. You can find the basis of A1, B1, A2, B2, and so on, where AI, BI, minus BI, AI equals 1 all frame. And also, when you take our differences, they all commute. And then quite, but except if delta happens to be plus 1, you have to change the combination of anti-commutation. And you find that BI, BJ, and BJ. But let's not go into technicality. Let's just concentrate on the case when delta is equal to minus 1. It's taking practically everything you can have in case 2. Suitable modification. But now what you find now is the following. If you choose as a basis, now here, normally I would describe like roots in white char, but we didn't time for that. So I'll just say, assuming you know what roots in white char are, they play a very important role in the analysis of the algebra. Turns out, if any canonical basis, then you can write down explicitly a so-called Cartan subalgebra, and in fact, it turns out that the things in this form, CI, AI, all of those commute with each other. And if you take the linear span of all of them, we call it the Cartan subalgebra. Then you can find all the weights, and then you find out the whole thing has what's called a weight space decomposition, where the individual weight is distinct of the BI, AJ, but are not equal to each other. And so you get the whole weight space analysis. You find the original B is a module for this Lie algebra, and the A's and B's in it are the weights. Well, that allows you to tell what structure is the algebra and so on. It's interesting. I don't want to go into that, but I just want to say, but now there's another thing you can do. You can also look, there's a whole lot you can say about this stuff, which I can't mention. But you can now go back and say, well, now let's look at the weights. Here, this Lie algebra is also represented an extra representation space. It is a Lie algebra operator operating on X. So what are the weights here? Well, there we anticipated, we looked at this on a very special case earlier. And what they are just, we choose a vacuum vector phi. If we can find a vector such that all the A is annihilated, then it turns out that if we compute all possible combinations Bj1, Bj, all possible products, I guess, Bjk phi, that those are all weight vectors. We've done all this. Then if you start to find out what they mean, it turns out to be very important in quantum field theory, and that's a whole lot of the everyday work of the non-conceptually minded physicists all appear in this context in a very straightforward way and can be used to. Well, let me say one final thing that when I try to do my approach to abstract quantum mechanics, the Impermitivity Serum, allows you to study various cases that physicists have never studied. Like an example of a space that only a finite number of points in it, and also various curved space versions and so forth. Those can all be explored. But it is especially to do the case of finite space, because then the main difficulties of quantum field theory disappear. Because the field now is a finite object and all of that. Well, that's something that I started to explore. I've never published anything on that, but I started to explore it way back in 1970, 24 years ago. But I just made this kind of thing just recently, and I'm now very encouraged to try this approach to look at that case. And what I'm hoping to do is to get really more insight into these mysterious things like Feynman diagrams, etc. And I should also state that the Feynman diagram approach, sometime after half a decade or so after Feynman, was picked up by the physics is not studying elementary particles in relativistic physics, but studying ordinary non-relativistic quantum mechanics of solids and structure of nuclei and so on. And they discovered that again, this approach, which essentially comes out of this kind of thing, is very effective. And what I'm doing now is having sort of put it in a form that I like. I'm now trying to see to what extent I can prove nice theorems that get their result. I mean, they have all these results by using these ideas in sort of a vague, clumsy way. And I'm hoping to find nice mathematical theorems, starting from this standpoint, which include the results. I would like to prove a few nice mathematical theorems which can then be applied to get a lot of the results on many body functions. And also, I have hopes of understanding. I have various hopes, I don't know how many you realize, but I've sort of found a handle on things that speaks to me, that I can work with. And I'm working very hard now trying to implement all of this. So